All right. That's because we know what absolute enthalpy is. What is absolute enthalpy? Well, what is H? In other words, what is enthalpy? You know, enthalpy increases. What is enthalpy? Tell me what enthalpy is. If enthalpy, I'm going from low enthalpy to high enthalpy. What is enthalpy?
So heat transfer at constant
Is
pressure.
enthalpy heat transferred?
What's energy?
Or gain.
So this is cold down here, and that's hot up there? Or it's hot down here, cold up there? So maybe this is just temperature?
Not temperature.
No, it's not temperature, because does the temperature change? It doesn't change. And so what is enthalpy? This is what we call absolute enthalpy. The reason is we've been talking about delta H. Delta H is okay. Delta H is just the energy. And it's the energy change. And the energy change can be in terms of, well, what can you do with the energy? Well, you could have it as heat and or work. And so in this case, this is endothermic. So I have to input heat and or work in order to get this to happen, because I'm going from lower enthalpy to higher enthalpy. And so is enthalpy, must be low heat and this is high heat? Is that what it is? No, that's not what it is, because this is delta H, and delta H is just this. And so what is enthalpy? You know, if somebody asks you, what is enthalpy, H? You know, if I have a low enthalpy, what does that mean? If I have a high enthalpy, what does that mean?
Yeah, high enthalpy means it has more energy that's able to be transferred. A low enthalpy means it has less energy that's transferable.
Okay, but we don't even need the transferable, because we don't have to transfer any energy. Let's say there's no energy transferred. Then let's just say I have enthalpy here. You know, all of a sudden, is this high or low? Well, it depends on what you compare it with. So inherently, is this high or low? Well, it depends on what you compare it with. Well, give me an answer. Is it yes or no? Is that a high or low enthalpy?
We don't know.
You don't know. There's no way you can answer that, because it depends on what you compare it to. It's like, oh.
Because internal energy is a state function.
Yeah. Well, what we know is that enthalpy is just the total energy, right, plus
Final. Total.
the
Work. It should be work.
Oh, PV.
not the work, but something that allow you to figure out the work. In case.
Oh, external pressure.
Yeah, the
volume
pressure
change.
volume state. It's the pressure volume state initially. And PV is actually energy, you know, atmospheres, liters, or liters atmosphere, or liters bar, bar liters. And so, in other words, this is the total energy. Enthalpy is just the total energy plus this PV state. And the PV state is, the reason we need to know the PV state is because that can change depending on, you know, if volume grows or volume shrinks, and that's going to require work by the system or require work by the surroundings. So the PV tells us how the internal energy interacts with the surroundings. I mean, how this whole picture interacts with the surroundings, whereas delta U just tells us how it interacts with the system itself. So this could be high or low depending on what we start off with. I mean, this is high if there's something lower here, or this is low if there's something higher here, you know, but in itself, it's just the total energy. Well, the problem is pressure is no problem, volume is no problem. The problem is U. We don't know what about U. Well, we don't know exactly how to calculate it or measure it, you know, accurately. In fact, you can't really measure it without having to destroy or break everything and do one gigantic calorimetry experiment in which we break this down to the very smallest parts. And so this is the problem. So absolute enthalpies are never determined, just delta H's are determined. Now, delta H is, we call it the heat, but the only reason we call it the heat is because we fixed the work. And so the remaining energy must be heat, but it doesn't have to be heat, right? It's just the energy. Well, if we don't worry about making any of the work, then it is the heat. And so it makes sense. You can just call it the heat. Well, anyway, this is the net. And so this is the net heat we'd have to add, or the net work we'd have to do, right? If we want to do it as work instead of heat. So this is the amount of energy we have to input in order to get this. Regardless if the system expands or contracts, all that's going to be factored in. Whereas in an exothermic reaction like this is the net heat evolved. The net heat evolved, again, we could just leave that as heat, or we could try to convert that into work, or just go straight into work. You know? Exothermic and endo. Enthalpy diagrams, this is what we're going to use from now on. We're not going to be doing internal energy diagrams. And so the enthalpy is just energy. You know, and higher energy, lower energy, that's all we have. And it's just total energy plus the PV state. So delta H for sure is going to be the most useful for us. So what are all the ways of determining delta H? Delta H is what we want. We want to know what the net cost is, or what we're going to get as far as net energy production. So delta H. Most of our reactions are done under constant pressure and P delta V work. And so in order to determine delta H, there are different ways. One, we could just do constant pressure calorimetry, the coffee cup calorimetry experiment. With constant pressure calorimetry, we measure QP. QP is just equal to delta amount times delta H. And so we can get delta H. Delta H is just QP divided by the amount. That's one way of determining delta H. Two, we could do constant volume calorimetry. If we do constant volume calorimetry, then what we're going to get is QV. QV does not give us delta H. QV gives us delta U. Delta U is going to be QV over the amount. But what we can do is we'll do a calculation, and that is delta H is just equal to the gross energy minus any work that was done. And then what we do with the work is you calculate this. You calculate W by how? Isn't W 0? In a bomb, yeah, it's constant volume. So how do I calculate W? I already know what W is. W is 0. So what am I talking about here, calculating W?
Delta H over delta U. No.
If the reaction, what you do is you calculate W if the reaction were done or was done under constant pressure conditions instead. And so the actual reaction was done under constant volume conditions. You did it on bomb, right? This is what we call bomb calorimetry. And so there was no work done in the bomb. But what you do in order to figure out delta H is you have to take the reaction out of the bomb, and then on paper you figure out what would the volume have changed if you had done the reaction outside the bomb. And that's what we do here. If we had done the reaction outside the bomb, then we could calculate the volume change. This is what we did on Thursday last week. We figured out what the volume should have changed in order to maintain constant pressure. And then we could figure out the work, and then what we do is we'll just correct the delta U that we got from bomb calorimetry with the work to get delta H, since we're most interested in delta H. That's 2. But calorimetry, coffee cup calorimetry or constant pressure calorimetry would be the best. Bomb calorimetry, it's okay. We just have to do some extra work to get delta H. Sometimes we have no choice, because if you're to burn something, let's say we're going to burn some sugar, then you wouldn't want to do that in the coffee cup, because not only the sugar would burn, but the coffee cup will burn as well. So I don't want to do that. And so there's some reactions that by necessity you have to do in a bomb. Well, that's okay, because we're going to correct it. Pretending if we did the reaction outside the bomb, we would have gotten this much work, therefore we can correct our experimental finding. Now, both of these require experimental work, and so, both of these are time consuming. But there are other ways of doing it strictly by calculation. That's Hess's law. Hess's law, we can avoid doing a calorimetry experiment and just figure it out. What we need, though, is we need some database reactions to work with. And so let's take a look at this here, Hess's law. This is setting up, the foundations for Hess's law. Hess's law works because delta H is an extensive property. That is, if I burn a mole of methane versus 2 moles, 2 moles of methane is going to give me twice as much heat. 3 moles of methane will give me 3 times as much heat. And so energy is extensive. So here's the combustion of nitrogen using oxygen, or the reaction of nitrogen and oxygen. If I form 2 moles of NO from 1 mole of nitrogen and 1 mole of oxygen, that costs me 180. If I double this and go with 4 moles of NO, so I get 2 nitrogens, 2 oxygens, gives me 4 NOs, then I double that, so I get 361 kilojoules. If I cut it in half, cut it in half, then I'm going to get half as much energy. So rather than the full mole, I use half a mole of N2, half a mole of O2, I'll get 1 mole of NO. It's 90.25 kilojoules. And so it's extensive. In other words, N times the reaction is equal to N times delta H. And so where N doesn't have to be an integer, it can be any fraction, whatever we want. All right, these are state functions. Whenever we have a state function, this is what happens. If I were to reverse the reaction, let's say, in the forward direction, I form NO. In the reverse direction, I decompose NO into N2 and O2. And so if it costs 90 kilojoules one way, then in the opposite direction, I'd release 90 kilojoules. So just change the sign. In other words, delta H of the reverse reaction is minus delta H of the forward reaction. So the first one we could summarize as N times the reaction is equal to N times delta H. Second one is delta H of the reverse is equal to minus delta H of the forward. When I have these, then I can do this. I can use Hess's law. What Hess's law says is that the sum of the steps is equal to the net. And so in this case, let's take a look at this. This is an enthalpy diagram. Start off with nitrogen and oxygen, half a mole of N2, a mole of O2. If I go straight from this to NO plus half O2 gas, it's going to cost me 90.25 kilojoules here. And to go back down, it's going to release 90.25 kilojoules. So I could take this as one step down. I'd have one big arrow going down, which would be negative 90.25. But what Hess's law says is that if I break down this one big step into smaller steps, then the sum of the smaller steps will equal the big step. And so the sum of the smaller steps is, there's one small step I could do here, which would be going from NO and O2 to NO2. That would release 57.07 kilojoules. And then from NO2, I could go to N2, half mole of N2 and mole of O2. That would be the remaining step. The remaining step is going to be minus 33.18. You know, the arrow's going backwards here, but if I've got to reverse it. And so these two smaller steps down is equal to this big step down here. Different ways of doing it. Okay, this is in mathematical form. And so in Hess's law, we add up the two small steps, we should get at the big step. They're solving this for something else, so this is not typically what we do. And so let me show you what we do in a standard Hess's law problem. Let's look at number 74. Carbon tetrachloride is an important commercial solvent. It's prepared by the reaction of chlorine with a carbon compound. This is a carbon compound, carbon disulfide. Determine delta H for this reaction. All right, so the reaction that we're interested in is this. Carbon disulfide liquid plus 3 chlorine gas produces carbon tetrachloride, ClCl4 liquid, and then this one, you know, which we'd call, using Chem 1A nomenclature, we call it disulfur dichloride liquid, but in organic chemistry this has a different name. So what can we do? Well, we want the delta H for this. We want to know, you know, what net energy is released or what net energy has to be input for this. You know, obviously there's work done because we're going from 3 moles of gas to no moles of gas, essentially. So we're losing about 75 liters of volume there. But we don't care about that because we're dealing with delta H. In delta H, we got to restrict it to constant pressure and P delta V work only. And this will be the amount of energy input or the amount of energy released in the particular reaction. And so we could do this by different ways. We could do this in a bomb. If we do this in a bomb, we would get delta U eventually and then fix the delta U, convert it into a delta H. Or we could do this in a coffee cup. We probably need a very strong, we probably wouldn't use styrofoam cups. We'd probably have something better to do it under constant pressure. Or we could just try to avoid going into the lab altogether. That is, if we have a database of reactions that we can choose from. And we do. Here's a little database of reactions that we can choose from, selected reactions. So let's take a look at these reactions here. So altogether, I have, I've got 7 reactions here. And so what I try to do in Hess's law is you figure out, is there a way to add up any combination of these reactions to get this net reaction here? Because what Hess's law says is this. It says delta H for the reaction is equal to the sum of the delta H's for the individual steps. You know, and I can add up a whole bunch of steps. And so if there's a way to add up these, now there is a way to add up them, but I don't want to add them up using an enthalpy diagram because that would be way too much of a pain. You know, if I were to go back and try to do this in terms of, you know, what do I mean by an enthalpy diagram? What I mean by an enthalpy diagram is this. I don't want to draw that out. It's too much work. Although technically this is what we're doing. Instead, this is the way you do this. Instead of doing that, what we do is we come up with a strategy. And the strategy is I want 1 mole of CS2. And so I look at this this list and then see, do any of these have CS2? Actually, this one does. In fact, this one has 1 mole of CS2. And a bunch of other stuff, but I don't care about the other stuff. All I care about is the CS2, so that's perfect. And so what I'm going to do is I'm going to just go ahead and write it down. So I'm not going to draw an enthalpy diagram, I'm just going to write out the reaction. CS2 plus 3 O2s yield CO2 plus 2 SO2s. And this is delta H1 here. This is reaction 1. And so I'm going to use reaction 1 as is. And so this is perfect. 1 mole of CO2, 1 mole of CO2, or CS2, sorry. What do I need next? I need 3 moles of Cl2. And so I look. Well, I got 1 mole here. I got 2 moles here. I got 1 mole here. So I don't have any with 3, but it's no big deal because I can multiply this by any number. Like if I use this one, I'd multiply this one by 3. If I use this one, I'd multiply by 3 halves. If I use this one, I'd multiply by 3. And so I have a choice here. And what happens is, do you know which one to pick? No, actually, I don't. I mean, there is some strategy I could use, but sometimes it's just a guess. And sometimes you guess wrong, but it's no big deal. You just back up and try again. But I'm going to try to use a little bit of strategy here, because if I multiply this first one by 3, I got it, right? I got my 3 moles of Cl2. But I could multiply this one by 3. Or I could take this one and multiply by 3 halves. Or I could take this one. Which one should I use?
The second option. Third one.
Should I use this one? Why not? Well, I'll tell you which one I probably don't want to use. Well, maybe it's a trick. Maybe they want us to pick the first one. Maybe the best one is the last one.
Well, is it because the products are on that reaction right there? The products of the.
Oh, you know what? I don't want to use. You know why? If I use the first one here, I'll get 3 Cl2s, but we'll also get 3 S2Cl2s. Do I want 3 S2Cl2s? No, I only want 1 S2Cl2, but so if I use the first one, I'm going to have to be going back and fixing it. So I don't want to use the first one.
Use the second one.
If I use the second one, does that screw anything up? Yeah, that's going to screw up the CCl4, right? Because then I'm going to get 3 halves CCl4, but I want 1 CCl4. So if I use this last one, let's take a look at the last one is not going to screw up anything. So I'm going to use this last one here. And so let's go ahead and do that. I'm going to multiply that one, which is called, what reaction is that? Reaction 1, 2, 3, 4, 5. Reaction 5. So I'm going to do 3 times reaction 5, which will be 3 SO2s plus 3 Cl2s. This is going to yield 3 SO2Cl2, and this would be 3 times delta H5.
I'm wondering why we can't just use like the first and the second equation,
We could.
because then you'd have 3 Cl2s and you'd have one of each of the products.
Yeah.
We could do that.
Oh.
There's more than one way of doing this, but I want to do it this way.
Oh, okay.
I want to do it this way because I want to show something. There's a reason I'm doing it this way. The reason I'm going to do it this way is because this gives us 3 Cl2s here. And so that's good. Correct? All right. And then we'll go on to CCl4. I want CCl4.
Use the bottom.
I use the bottom one. This is what, reaction 7?
Mm-hmm.
So let's go ahead and use that one. But I actually have a choice. Because do you see, I could use the bottom one here, or I could use this one and just reverse it. But this is easier because this is already right. And so this will be reaction 7. This will be CCl4 plus O2 yields COCl2 plus Cl2O. Now all I worry about, this is wrong because this CCl4 is on the wrong side. I need a CCl4 on the product side.
No second one, no third one.
And so I don't want this one. I could use this one if I switch it, reverse it, but you know what? Why bother? Because this one's already correct. And so let's go ahead and use reaction 3. So if I use reaction 3, I'm going to get CCl4 goes to C plus 2 Cl2s. And so this is the reverse of reaction 3. And so I'll just use the negative sign here. And this will be negative delta H3. And so this is, did I screw it up again?
Yeah, you're just supposed to write it down. As
No,
is.
I was supposed to write it up as is, sorry. So this is going to be C plus 2 Cl2. Eventually we'll get there. You'll see that even though it looks all mixed up because we're getting lots of different stuff, it's good. And so the strategy is you ignore everything else. 'Cause eventually everything else should just work out. And so what we're going to get here is we got our CS2, 3 Cl2s, our CCl4. And so that's good.
What about our
There's an extra CO2 though, or 2 extra ones.
Oh, shoot. You're right. That screwed it up. But I'm not going to worry about it yet. We'll worry about it after we get our final product. Our final product is,
That's just
that's 2 Cl2. And it looks like if I use reaction 2 as is, that'll work. So I'm going to use reaction 2 as is. 2S plus Cl2 gives us S2Cl2. And this is going to be delta H2 as is, right? And so now we got it. I have my CS2, Cl2, CCl4, and S2Cl2. Except there's some problems here. Well, let's take a look. Hopefully, if this works out, then that's all you have to pay attention to. Because if this works out, everything else should cancel out. And so let's see, does everything else cancel out? Well, I have 2 SO2s here, and I have 3, so I'm left with 1. Does anything else cancel out?
where did that come from? Could you repeat that last part?
Okay, so I formed 2 SO2s here, I have 3 SO2s here, so 2 SO2s will cancel out on both sides.
Okay.
Can I cancel anything else out? No, I can't cancel anything else out. And so now I have to think, I got to cancel, what else do I have to cancel? I got to cancel out a lot of stuff. And so let's cancel out this one. Because this one looks to be the most difficult one to cancel out because it's got 3 elements, sulfur, oxygen, and chlorine. So in order to cancel this one out, I need 3 SO2Cl2s on the left side. So what's going to give me SO2Cl2 on the left? Nothing here. Oh, but I have SO2Cl2 here. And so in order to cancel out these 3, then I'll reverse this reaction and multiply it by 3. But if I reverse that reaction, multiply by 3, then isn't that just... So what I'm doing is I'm just undoing what I just did, right? If I undo what I just did, then I didn't need it. Okay? And so basically what I'm going to do is I'm going to just cross it out. And so basically we end up with 2 Cl2s plus 1 Cl2 gives us 3 Cl2s, which compensates for that, and we don't have this SO2Cl2 that we have to deal with. And so like Manny said, why didn't we do this from the beginning? Why didn't we do this from the beginning is because it doesn't matter what your approach is. If something doesn't work out, you just back up and start it over again, because if this works out correctly, then everything should cancel out. Everything else should cancel out. And so let's take a look. Well, it doesn't, does it? Because I have 2 SO2s here, I have no SO2s here. And so I have to cancel that out. And so does that mean I'm going to have to reverse this reaction and add it? If I reverse this reaction and add it, then I'm back where I started. And so let's take a look here. When we take a look here, we're lucky, because in this case we have reaction 1 that has an SO2 and reaction 4 that has an SO2. And so this way we don't have to reverse reaction 1 and then do what we just did. In this case, what we're going to do is we're going to reverse reaction 4 and then add that. Except what we're going to have is we're going to have to multiply it by 2. And so what we'll do is we'll do this. We're going to do minus 2 times reaction 4. And so if we do minus 2 times reaction 4, we're going to get 2 SO2s, which yields 2S plus an O2. And so now the 2 SO2s cancel out properly, and I didn't have to undo reaction 1. Now, let's see what else we got here.
2S.
Well, the 2S cancels out. That's nice. And the O2, but not enough O2s canceled out. Only one of them. That leaves me with 2 O2s. There. And then I still got this CO2 here that I have to get rid of. And so let's try to get rid of the CO2, because that's going to be harder to get rid of than the O2. And so what I need to do is get rid of the CO2. Well, one way of getting rid of the CO2
So we need just the opposite of
is I could do,
It's 102. Because there's 2 reaction cores, right?
So 2S.
oh, yeah, it's 102, you're right. All right, 102. So in order to get rid of the CO2, I have 2 choices. One, I could reverse reaction 1, but if I reverse reaction 1, then I just undo it, right? It wouldn't make any sense. So there's got to be another reaction with CO2 that I can use, otherwise I can't make it work, and that would be reaction 6. So if I reverse reaction 6, then that would be minus reaction 6, which would give us
CO2.
CO2 goes to C plus O2. And this would be minus delta H6. And so then that's going to get rid of the CO2s. I got a CO2 on the left, a CO2 on the right. And then it gets rid of the carbon. So I got a carbon on the left, carbon on the right. And it gets rid of the remaining O2. And that leaves me with only the species that I want. You see how it all works out? It all works out. If it doesn't, then it's easy. You just try different things until you get it to work out. And so these has a lot of problems, even though this seems like a lot, you know. None of them are hard because eventually you'll get it.
So is the answer the sum of H3 and H2?
Okay, this is what we're going to do. We add them all together. And so the net reaction, let's just make sure we have the correct net reaction. The net reaction here is going to be CS2, which we have here, plus 3 Cl2s, we have here, yields CCl4 plus S2Cl2. And so delta H of this, using Hess's law, is the sum of the steps. And so the first step is delta H1. The second step is delta H3 plus delta H2. I forgot to write this one. This is going to be minus 2 delta H4. And so this is going to be plus a minus 2 times delta H4 plus a minus delta H6. And so we just add them up. Delta H1 is minus 1077. Delta H3 is minus 135.4. Delta H2 is minus 58.2. Delta H4 is minus 296.8 times 2, and then change the sign. And so that would be 592.6, 593.6 plus 593.6. And then minus delta H6 would be plus 393.5. And just add it up. Now, I didn't, you know, sometimes on tests I give this and then a lot of people start it and then they get stuck and then they get into a tangled mess and they can't get unstuck. And so, and the reason is once you get into something that's a tangled mess, then just start the problem over again. Start the problem over again and go down a different way, because you would be surprised. You know, you would think everybody would get it and it'd be 100% problem, but it's always like 20% or more don't get the answer, can't figure out the answer, which happens. And so even though it looks confusing and you can get confused and mixed up, it's not hard. Just keep that in mind. Just keep at it, okay? All right, any questions on this? Now, if we had to do enthalpy diagrams, it would be hard. You know, if we had to do enthalpy diagrams and show this as this, it would be a pain. This would be a true pain.
And we'll have 5 arrows going up.
You'd have all kinds of arrows. We aren't going to do it in terms of enthalpy diagram. But you know, this isn't the easiest. Actually, there's a much easier way of doing this. And that is, we're using any reaction here. Any reaction here is going to have different, products. Like here, we've got CO2 and SO2, and different reactants as well. But if we restrict ourselves to one type of reaction, then Hess's law becomes extremely easy. And the type of reaction, if we restrict ourselves to only formation reactions, then this is hard by comparison. This is way harder than this. And so when I have this little f here, that means formation. And what does formation mean? Formation is defined as this. It's the formation of 1 mole of substance from the elements in their standard states. Okay, so by definition, the standard enthalpy of formation of a pure element in its reference form is 0. And let's take a look at different formation reactions. So if I look at delta H of formation for something like oxygen gas, then what this is it's the formation of 1 mole of oxygen gas from the elements in their standard state. The standard state is the most stable state. So the standard state of H2O at room temperature is H2O liquid, not H2O gas, not H2O solid, but H2O liquid at 290 Kelvin and 1 atmosphere. That could change, you know, if you change the temperature or if you change the pressure. Well, for oxygen, let's say we're dealing with 290 Kelvin, this is the temperature of interest, and 1 atmosphere. Well, then oxygen would be O2 gas here. And so we're going to form 1 mole of O2 gas at 298 Kelvin from 1 mole of O2 gas at 298 Kelvin. What's the energy change? There's no change. And so delta H formation is 0. That's going to go for any element in its standard state. What's the standard state of carbon at 1 atmosphere and 298 Kelvin? 298 Kelvin being temperature of interest, but not standard temperature. The standard state of carbon at 1 bar and 298 Kelvin is graphite. And so delta H of formation of graphite is 0 because we're going from 1 mole of graphite to 1 mole of graphite at 298 Kelvin. But delta H of formation of diamond isn't 0. Delta H of formation of diamond, because diamond is not the standard state of carbon. The standard state of carbon is graphite. And so in this case here, this should be delta H of formation. And there should be a little superscript here. This is slide number 45. So this is a typo. They forgot it. So this is I'm not fixing all these. I'm just using them as is because you might as well do some work with PowerPoint. That's the problem with PowerPoint. Sometimes you don't have to do anything. And so it's a little easier to remember if you have to add some details in there. And so delta H of formation of diamond is 1.9. This is a formation. Can you tell? How can I tell this is a formation reaction? Because we're forming 1 mole of diamond from carbon in its standard state. Standard state of carbon is graphite. So 1.9 kilojoules. 1.9 kilojoules, some people probably use that to make their coffee this morning. So all I have to do is get some graphite, like that pencil lead there, and add 1.9 kilojoules. That's so easy. That is so easy, isn't that? Boy, I can make diamonds so easily. 1.9 kilojoules is nothing. The problem is these are state functions. State functions just tell you the final and the initial. They don't tell you how it gets there, right? And so the problem is the path. Yeah, sure, that's the energy difference, but the path for this is very difficult. It's not so easy to convert graphite into diamond. But that would be the energy input, the net energy input. But when you look at the path is quite a bit different. Okay. Let's continue on here. What's the standard state of bromine? Bromine is a liquid at 298 in 1 bar. And so bromine's a liquid. Therefore, delta H of formation of liquid bromine is 0, but delta H of formation of gaseous bromine is about 31 kilojoules. In other words, here, this would be the standard enthalpy of formation of bromine gas. In other words, this just looks like evaporation or vaporization or boiling, liquid to gas. And so, in other words, we have to vaporize the bromine liquid. It's going to cost us 31 kilojoules per mole. Here's some other values for this standard. In fact, this is an excerpt from Appendix D. Appendix D is going to have a more comprehensive list. So here are some common ones here. C2H5OH, you know what that is? What alcohol is this?
Ethanol.
Ethanol. This is ethanol, 2 carbons. Methanol is right about it. The standard enthalpy of formation is minus 277.7. Okay, that's how many kilojoules per mole. What is the reaction? Can you write the reaction for me? The reaction is not written. It's not written because everybody should know what it is. So let's do one really quick. Yeah, you'll have to figure it out. So let's do CO. Delta H of formation for CO, carbon monoxide gas, is equal to minus 110.5 kilojoules per mole. The reaction that this is associated with, the formation reaction, is the formation of 1 mole of CO2 gas from the elements. Well, what is the standard state of carbon, the element? Is it diamond or graphite? Well, it's graphite. And so we'll have 1 mole of graphite. And what's oxygen? What's the standard state of oxygen? Is it O or O2 gas or O3? What is it? It's O2. And so we're forming 1 mole of substance from the elements in their standard state. Well, these are the standard states of the element. We'll balance it, and we'll need 1/2 an O2. This is the reaction. For this reaction, the delta H for this reaction is minus 110.5 kilojoules for every mole of carbon monoxide formed. And so, can you write the reaction for ethanol? The delta H formation reaction for ethanol?
It's 2 carbons. What's the standard state of oxygen?
H2 gas.
H2.
Gas. Just for hydrogen, yeah.
It started off pretty boring.
Why don't you just say that C2H5OH becomes H2? You see what I'm going with there? Or no? And then you just do each of those.
Who's gonna break it down like that? But yeah, you could. No, cause it. Oh yeah, you do the reverse guy.
So-
H2O, yeah.
Force it in there.
You said that.
Because it's H2O plus.
African.
All right, so does
yeah,
somebody
I'll
have
do
it?
It's a combustion.
You can bust
All right, so we're looking at the delta H of formation for C2H5OH liquid with pure ethanol, minus 277.7 kilojoules. So what is the reaction or process involved in that enthalpy change? What are we starting off with? What are we ending with? It's an enthalpy change.
You can start from.
This is not the absolute enthalpy. This is a change. Delta is always a change, right?
Mhm.
We could have the absolute enthalpy of ethanol. We wouldn't be able to calculate it, though. And so what's the initial? What's the final? Someone figure it out? No?
Can you?
Or this is a change or process or reaction. So the definition of formation is this. It's the formation of 1 mole of ethanol from the elements in their standard state. And so I got 2 carbons. I'll need 2 graphites, 2 carbon graphites. I got 6 hydrogens, so I'll need 3 H2. H2 would be the standard state of hydrogen, plus 1 oxygen, so I'll need half an O2. And so this would be the reaction, or this would be our initial, this would be our final, and the change in enthalpy, the change in total energy plus the PV state would be minus 277.7. This is under standard conditions, so that would be delta H. Standard conditions for this just means that the gases are 1 bar or 1 atmosphere. So it's exothermic. We're going to see that not all of these are exothermic. You know, some things are more stable than the elements, some things are less stable than the elements. And so this is just showing the elements at 0. And so things like C2H4, which would be ethane, C2H2 acetylene, these are less stable than the elements. These species are more stable, like butane, propane, methane, these are more stable. And so some things will have an exothermic delta H formation, some things will have an endothermic, some things will have a delta H formation of 0. Anything, you know, that has equivalent energy of the elements, which would be the elements themselves. So these are some standard enthalpies of formation. Well, that's a small list. A big list of these are in Appendix D, Table D. So let's take a look at Table D5, or is it D5? No, D1, I think. Table D. And look at some of the entries in here. All right, here's Appendix D. If you look over here, the temperature is 298.15 Kelvin, but that's because this is the most common temperature. It's not because it's under standard conditions. And under standard conditions, I can tell by the little superscript here. And so under standard conditions means that the substances are at 1 bar here, bar, pressure. And for aqueous solutions, the solutes are at unit activity. Activity I'll talk about later, but unit activities we can just take as 1 molar. And so the gas pressures are 1 bar and the solutions are 1 molar. Okay. We have data for ions in aqueous solution relative to values of 0 for delta H formation, delta G of formation. Delta G is Chem 1b, and S is Chem 1b also. Shoot, out of time? I'm going to have to finish this tomorrow and then start chapter 8. So we're going to have a lecture kind of lab thing tomorrow.